On Christmas morning of 2021, something spectacular happened. A powerful rocket awoke, soaring swiftly and cutting through the cloudy skies towards the darkness of deep space. Its destination? A point 930 million miles from Earth, a location where the gravitational forces of the Sun and our planet meet uniquely. At this place, known as the Lagrange point, the payload would remain fixed in relation to Earth while orbiting the Sun. Just imagine, immense panels unfolding to shield the payload from solar glare, while segments of hexagonal mirrors opened and locked into place. And then, after several months, the wait for the ideal temperature, as cold as the depths of space. When it was finally ready for operation, a signal was sent from Earth. The James Webb Space Telescope, after 30 years and $10 billion invested, was ready to open its eyes and dive into the depths of the cosmos. Astronomers expected to see just small stellar groupings in the images from the early cosmos. However, what they saw were large, well-formed galaxies peering into the darkness. Imagine traveling back in time to when Galileo Galilei first pointed a telescope towards the sky. Back then, the main uses were for navigation, topographic surveys, and of course, wars. But Galileo had other plans. He was fascinated by celestial movements. And then, in a major debate in 1921, two giants of astronomy, Harlow Shapley and Heber Curtis, fervently discussed the true nature of spiral nebulae. The answer? It had to wait for the genius of Edwin Hubble, who with a 2.5-meter telescope showed that yes, these nebulae were far beyond the Milky Way. The quest for answers did not stop. Ever larger telescopes were built, and the Hubble Space Telescope, launched in 1990, gave us an unprecedented view of the cosmos. And just when you think you've seen it all, along comes the James Webb Space Telescope, launched on Christmas morning of 2021. But how do we travel back in time to understand the origin of galaxies? We need to unravel the earliest moments of the cosmos, a time dominated by quantum mechanics where quantum energy fluctuated, popping in and out of existence. During the brief period of cosmic inflation, the expansion of the universe accelerated, freezing these quantum ripples in space. At the end of inflation, these ripples were filled with the matter that makes up the cosmos today. And as the universe cooled and expanded, the first elements began to form. And so, gravity began to shape matter, pulling hydrogen, helium, and even the mysterious dark matter into denser regions. Over billions of years, galaxies underwent many transformations, accumulating stars and gases, and even in the most catastrophic supernova explosions, they continued to recycle matter to form new generations of stars. Did you know that each generation of stars contributed heavier elements, chemically enriching the universe? It was 1932, and Carl Yansky was puzzled. In the early days of transatlantic radio communication, the world was already accustomed to transmitting voices over thousands of miles. But there was something about the signal that Jansky heard that intrigued him. A persistent background hum marked the transmissions. It wasn't the existence of this noise that disturbed him, but rather its impeccable punctuality. Why did the noise vary with the hours of the day? How could his equipment know the time he was making his measurements? As Jansky's observations stretched over days, weeks, and months, he noticed that the static was not aligned with the 24 hours of the solar day. The shift in the noise was slow but constant, sliding across the sky, seemingly synchronized with the sidereal day, the time it takes for distant stars to complete a turn around the Earth. The difference was small, just 4 minutes, but the implications were profound. At that time, many astronomers scanned the skies with their telescopes, focused on the optical light emanating from stars and galaxies. However, Jansky realized that another form of electromagnetic radiation was arriving from the universe. Thus was born the era of radio astronomy. Soon after, radio waves from the sun were detected in the United Kingdom and the USA. In the United States, Grota-Robert built the first true radio telescope, remaining as the only radio astronomer for a decade. He made it clear that our own Milky Way shone in this new light. Later, maps of the radio sky revealed powerful sources of radio emissions, radiating from tiny points scattered across the sky, leading to the discovery of the first quasars. Astronomers discovered that these are fed by supermassive black holes, with masses exceeding 1 billion times that of our Sun, so powerful that we can see them from vast distances, traveling back in time for more than 10 billion years. These supermassive black holes, it is thought, formed from the teeth of supermassive stars. After feeding and merging, they became the central gravitational point of many larger galaxies. Thus, in the first few billion years, the universe blazed with activity. The flames of the first stars, the first galaxies, and the first quasars shone intensely. But after that early era, the youthful vitality began to fade, and cosmic activity began to calm down. Over the last 10 billion years, although the rate of star formation has steadily declined, galaxies continued to evolve and change, driven by the pull of gravity. Smaller galaxies grew into large galaxies, while the latter swallowed their cosmic neighbors. Some galaxies were completely shaped by their spin, while galactic-scale gases cooled and collapsed into a flattened disk, fragmenting into stars. This immense disk of constantly spinning stars became the defining feature of these galaxies, the beautiful spirals we peer at through our telescopes today. However, for other galaxies, the journey to spiral beauty was interrupted when collisions with more massive galaxies violently tore them apart and stole their spin. Instead of settling into rotating disks, they were transformed into more amorphous objects, the elliptical galaxies, another main type of galaxy observed in the skies. It is estimated that there may be 1 trillion galaxies in the observable universe, varying enormously in size, from tiny to immense, most of them small, while the largest known is over 200 times more massive than our own Milky Way. One of the most surprising discoveries of the last century was not just the galaxies themselves, but also the realization that galaxies are not simply scattered randomly through the cosmos. Through the action of gravity, the quantum seeds imprinted in inflation shape themselves into a complex network of masses known as the cosmic web. Subdensity volumes are emptied, with matter drawn to more massive regions, while some galaxies and dark matter remain in these sparser regions, which can stretch for millions of light years. Matter flows out, gathering in immense sheets and filaments, and continues to be drawn to the most massive objects in the cosmos. But where are all these galaxies going in their journeys out of the voids and through the sheets and filaments of this complex network in which dark matter is distributed like a sponge? There are superdense regions, the galaxy clusters. Galaxy clusters are incredible places, some housing many thousands of galaxies. These galaxies churn in immense halos of dark matter that far outweigh all the stars, the greatest concentration of mass in the entire universe, and at the heart of these clusters are true cosmic monsters, the central cluster galaxies. These true giants of the universe, built from hundreds of trillions of stars wrapped in an immense amount of dark matter, are cosmic behemoths. They are deeply rooted in the gravity well and are surrounded by thousands of other galaxies. As we move further away, astronomers have discovered that the clusters themselves cluster, joining in even more immense structures called superclusters. In our part of the universe, we seem to be embedded in the Laniakea supercluster, home to many millions of galaxies. Just as galaxies vary enormously in size, so do galaxy clusters. They are typically home to 1, 2, or a handful of larger galaxies, similar in scale to our own Milky Way. With them will be a host of smaller galaxies, possibly hundreds of dwarfs, all linked together by mutual gravity and the dark matter that accompanies them. Indeed, our own Milky Way lives within one of these groups, a group we share with the Andromeda Galaxy, and this local group, as it is known, contains a wealth of other galaxies, some of which are visible to the naked eye, notably the Magellanic Clouds seen in the southern hemisphere. But more than 100 other galaxies are held in the gravitational grip of this local group. Most of these smaller galaxies only came to light in the last few decades, revealed in deep surveys with new telescopes that peer even further into the darkness. Since the 1990s, it has been realized that the Milky Way is consuming several other dwarf galaxies and is constantly growing. Andromeda is also enshrouded in the debris of 2 galaxies recently consumed. The feeding that began many billions of years ago continues today. Astronomers call this phenomenon galactic cannibalism. But did you know that measuring how fast the universe is expanding today was one of the great debates of the 20th century? With the help of the Hubble Space Telescope, a consensus emerged with the Hubble constant established at approximately 72 miles per second per million light-years. So, now that we have one of the key values, what about the content of the universe? Well, that was the tricky part. Astronomers knew there was more to the universe than visible stars. The rotations of galaxies and the movements in galaxy clusters show that most of the mass of the universe was dominated by the enigmatic dark matter. And as dark matter is almost impossible to observe directly, astronomers had to be creative. In the 1990s, 2 teams used the light from exploding stars as beacons to map cosmic expansion. But here comes the twist. They expected the expansion of the universe to have slowed down due to the presence of matter, but that's not what the data showed. So what was accelerating the expansion? The answer: dark energy. And not just the presence of this energy was surprising, but also its amount, accounting for about 70% of the cosmic energy budget. And that's where James Webb comes into this whole story, showing us that the early universe was perhaps more complex than we imagined. Despite the initial alarming claims, adjustments in the models can explain the recent observations. Maybe the initial models were wrong? Maybe the first galaxies burned brighter than expected. So, intrigued? The truth is, we are still discovering our cosmic home. Don't forget to like, subscribe, and comment what you think about this journey through the universe. See you next time.